Here's a question where they give us an exponential equation and they ask for many features of the graph. What is the vertical intercept? What is the horizontal intercept? What's the domain, the range, and try not to confuse the difference between the horizontal intercept and the horizontal asymptote. So it turns out that these last four, the answers that I'm going to give are true for any equation of the form y equals ab to the x, provided b is bigger than 0. Or a lot of this would change, and technically b couldn't be 1 as well. If b is bigger than 1, you'll get exponential growth, and if b is smaller than 1 but bigger than 0, you'll get exponential decay. So those are the only b values that we consider. The vertical intercept is where the graph crosses the vertical axis, and one thing that's always known about the intercept, where the graph actually crosses the vertical axis here, is that you would move 0 units in the x direction to plot that point, and the output would be to be determined. So that means to find the vertical intercept, you replace x with 0. In fact, one of the definitions I give students for the vertical intercept is the output you get when you plug in 0. It always boils down to be the a value here. So let me show you why. So if I was to replace x with 0 here, then what I would get, it turns out that any number, with only one exception, any number to the 0 power turns out to be 1. You can check that on your calculator. You should know that 0 to the 0 is undefined, but any other number that you know of raised to the 0 power gives you 1, and 142 times 1 is 142. So because any number to the 0 is 1, you could do it in general here. You could take y equals ab to the x, and you could replace x with 0 here, and I could argue that since any number, with one exception, since any number to the 0 is 1, you'd get y equals a times 1, or just a. So that means that for any equation, provided these conditions are met, when you plug 0 in, you always get a. So you could actually even put that in here, is that the vertical intercept is always 0, a. So that's a lot of explanation to simply say they gave us the vertical intercept from the beginning when they wrote 142 there. So let me show you what happens when you graph such things. Here I've graphed our function, and I actually pasted it over here so I can talk about it later. So here's the graph of our function, and as long as b is bigger than 1, you're going to get exponential growth. But notice what I said here is true, that the 142 produced the vertical intercept right there. In fact, I could change this now. Suppose I wanted this graph to cross at 40. I could change this to simply 40, and notice the graph would have a vertical intercept of 40. So this over here does indeed control the vertical intercept. If you want 60, put a 60 there, and it'll pop up to 60. But for our example, that was 142. So what happens here is the graph has a y-intercept of 142, and if you were to step 1 unit to the right at x equals 1, what would happen is your outputs would increase by 12%. So this is classic exponential, where it just skyrockets, and that behavior continues forever. So even though it looks like it has a vertical asymptote here, it doesn't. So I'm just going to go by here and one by one explain each of these, but it relies on the fact that you understand that as long as b is bigger than 1, you're going to get this rough shape no matter what. It's always going to level off to be the x-axis on this side. It's going to grow exponentially, and the vertical intercept is going to be based on that. How fast it grows depends on the growth factor here. In fact, if I wanted this to grow slow, I could change this to 1.02, and you see that the curvature is not near as great. So I pasted a couple graphs from Desmos.com here to show you the two possibilities. If A is positive, that means your vertical intercept is above the x-axis, and B is bigger than 1, you're going to get a graph that looks like this, regardless of the actual numbers you choose. So my A is 142, so it's positive. So for our example, it's 142. And if b is bigger than 1, which it is, our b value in y equals ab to the x is 1.12, which is bigger than 1. So I'm going to argue that the last four questions here are actually true regardless of the a and the b, as long as it meets these conditions. So if a was positive and b was between 0 and 1, meaning positive, bigger than 0, but smaller than 1, means your graph would decline like this. And notice they both have a horizontal asymptote here of y equals 0. Let me argue the horizontal intercept and the horizontal asymptote. This actually takes quite a while to explain, but to give you some idea what's going on, it's easier to look at this graph. Now, I don't believe that I graphed this with a b-value of 0.5, but it makes it easier to explain. Imagine if you had some quantity. I can't even see what that number is. I think it's 142. So, and you were to cut it in half. Imagine that you, every time x increased by 1, you cut it in half. It would go down, and you cut in half again, and you cut that y value in half. Basically what happened is your y values would get smaller and smaller and smaller, but never hit 0. So the fact they never hit 0 means your horizontal intercept does not exist. Remember, if you're looking for a point on the horizontal axis, you're looking for an x value that makes the output 0. That's the definition of a horizontal intercept, and it turns out with exponentials, with these conditions being met, that never happens. It never actually reaches 0. It would be like taking an apple and keep cutting it in half, take that half and cut it in half. Theoretically, at least mathematically I should say, you never reach a 0 apple, it just gets infinitely close. So there is no horizontal intercept, so I'm going to write does not exist, and that actually answers this down here. There's no horizontal intercept, but there is a horizontal asymptote. The idea of a horizontal asymptote is a horizontal line for which the graph gets infinitely close, and in this case never touches it. So the idea is if these conditions are met, it doesn't matter if b is bigger than 1 or between 0 and 1, you're going to get an asymptote. Basically that's the x-axis, and the equation for the x-axis is the horizontal line that cuts through y equals 0. So its equation would be y equals 0, and we call that a horizontal asymptote, and that's the same over here. And that's going to be true regardless of the a and the b that you pick, as long as these conditions are met. So I'm going to say y equals 0 there. Now, the domain and the range, again, are the same regardless of what's going on, as long as these conditions are met. I'm going to start with the domain. The domain is what kind of x values you can plug in and expect to get out valid y values. And it turns out that you can plug in anything. In terms of graph, you usually ask yourself how far left the graph goes, and it's kind of obvious in this case that it goes left forever. It's not as obvious, however, that it goes to the right forever. In fact, you may actually think that there is a vertical asymptote here, that there's a limit for which you can no longer plug in x values, if you will, that the graph goes so steep that you'll never get an x value, say, of 20. So I don't know if you can see this, but this is 20 here. So the idea is if you thought that the domain was limited, I'm arguing that it's all real numbers. If you were going to argue the domain was limited, you'd be saying that there's an x value for which you cannot plug in any x value bigger than that. So I'm not sure what you want to assign this number, maybe 1 or 2 or something like that. But it looks like the graph goes vertical and doesn't exist to the right of that. But I argue the graph does go to the right forever. It's just it grows so fast you can't see it. So to argue the reverse, play devil's advocate, if you thought there was a limit to how far to the right it went, I would simply plug in 20. And it would be the case that you'd get the number that would be obtained by taking 142 and increasing it by 12% 20 times. Take your calculator and do that. If you get an error, it'll only be because it's an overflow error and your calculator can't calculate a number that big. So it turns out it goes to the right forever. And in this graph, it's obvious that it goes to the right forever. Not obvious that it goes left forever, but for the same story, if you were to argue there's a limit for which the graph doesn't go left of that, I'd simply always plug in a number smaller, more negative, and you'd see that you get an answer. So by somewhat memorization, I know the domain of an exponential, if these conditions are met, are all real numbers. Now, I can't say all real numbers on this one because the directions were to write my answer in inequality notation and interval. So in inequality notation, since we're talking about the domain, you would say that x is bigger than negative infinity, and at the same time x has to be smaller than infinity, which basically means everything. This is just a fancy way of saying all real numbers. If you wanted to put that together into a compound inequality, you would write the negative infinity first, less than x, less than infinity. It would mean the same thing. It would mean that x is less than infinity and at the same time bigger than negative infinity. And the convenient thing about that notation is when you go to write it in intervals, so this is inequality notation. Interval notation would be almost exactly the same. You put the negative infinity, except you don't write less than symbols and you don't write the letter x, you just put comma infinity. Given the fact that it's domain, we just assume that you're talking about x values because that's the input variable that was given. And then since you don't ever actually take on the value of infinity, we put parentheses. If you ever had a number that you do want to include that in the domain, you'd put a bracket. So there's the answer for domain. The range would be the set of y values. So what kind of y values does this graph take on? And we already talked about that. And it's kind of obvious that both graphs go up forever. So that both graphs go up to infinity, approach infinity if you will. let me say it that way. But they don't go down forever. If you like my example of taking an apple and cutting it in half successively, it gets closer and closer to 0 but never reaches 0. So your y values are limited. The lowest that it would ever go is infinitely close to 0 but doesn't actually hit 0. So the range, simply put, would be y values bigger than 0. And then in interval notations, put your smallest and your largest. So 0 is the smallest y value, comma, and there's no limit how high the graph goes, so I'm going to say that's infinity. And you never actually take on a value of infinity, so I'm going to put a parenthesis. And in this case, like I said, you never actually take on a value of 0 mathematically. So I'm going to put a parenthesis there. So there's my interval notation there.